Hi everybody, I'm Michelle Maharbiz.
And I'm Tom Zaidel.
And today we're doing the Wheatstone Bridge. So why are we doing the Wheatstone Bridge, Tom?
We're doing the Wheatstone Bridge because we have a variable resistor that we're interested in measuring a response from. And the Wheatstone Bridge takes a change in resistance and changes it into a change in voltage.
Okay, so that's right. We've got this resistor. We want to sort of change that resistance into a voltage that our little robot brain can read. Now, conveniently, it's also a great way to practice our KVL, KCL type of circuit laws. And we'll need those very readily when we do amplifiers, so this is a good way to brush up. Okay, let's get started. So here's the Wheatstone Bridge. Here's the circuit. And I'm going to walk you through sort of the basics of it, the layout, and some observations before digging into the math a little bit. So notice, first of all, there's a DC voltage source here that sets the voltage between these 2 points on the resistor network. So you can think of this Vin as some fixed, non-changing voltage that the circuit provides for you. It could be a battery or some voltage source, and you'll see in the robot where this comes from. But we've also got 4 resistors. So we've got R1, R2, and R3, and they're connected effectively down 2 branches. So you've got this left branch, and they share a node here, and then you've got this right branch, and they are connected there. And the last piece that matters is that we're actually going to be interested in measuring the voltage, and we call this the V out, or the output voltage, between these 2 points here. Okay, and we've labeled them plus and minus, and we'll get into that a little bit later. So first observation, V out must depend or be a function of V in and the 4 resistor values. Okay.
And it looks like this function is very important because it's our input-output function. If we know exactly the form of this function, given an input voltage and 3 of the resistor values, we'll be able to detect what the 4th resistor value changed based on what V out is.
That's right, that's exactly right. Vn is constant and 3 of these resistors don't change, but let's say the 4th one is our variable sensor resistor, then as that one changes, our V out will change.
So R4 in our case will be our flex resistor.
This is going to be our whisker flex resistor. Okay, so let's get started. So we're going to look at this in 2 parts and work slowly through how KVL and KCL are used for this, and then we'll put it all together and give you sort of a few thoughts before we move on to the next thing. Okay, so just 1/2 of the Wheatstone Bridge is a very useful construct to know, and it's called the voltage divider. And so we're going to go through that. For its own sake, it's actually very useful to sort of have the voltage divider intuitively. Okay, so I'm looking at just a piece of this Wheatstone Bridge, and I want to analyze it. I want to understand the current flowing around it through the resistors. I want to know potentials across the resistors. What do you think I should do?
Well, a good place to start is with what we know. So let's start with Kirchhoff's voltage law.
KVL. Okay, so what do I do? What do I want to do first if I want to write a KVL equation?
Well, first let's identify all the voltages that are in this loop.
Okay, so let's label some voltages. So we've got the battery voltage labeled for us. That's pretty good. And I'm going to make labels for the other 2 components, which are resistors. I'm going to call this one VR1. I'm going to call this one VR2. And these are arbitrary. In other words, just because there's a plus here and a minus there doesn't mean there's plus charge on one side or minus charge on the other. The reason I'm going to label them is because we're going to need to use Ohm's law. And so to remind you of Ohm's law, if I have a voltage across a resistor that I define as V, and the current is going from the plus to the minus, and I call that current I, and the resistor value is, let me write that here, kind of crowded, R, then Ohm's law tells us that these are related in this way, okay? And so by labeling them, I'll keep my minus sign straight. Okay, so now I've labeled all 3 things on there. How do you like to do KVL?
Okay, well the way I like to do it is start somewhere and then think about voltages as changes in elevation.
Okay.
So let's start at the minus terminal of the DC source.
Okay, we'll start here.
And it looks like we go from minus to plus, so we are moving up in voltage by Vn.
Okay.
Then as we move on to resistor 1, we go from plus to minus VR1. So we're decreasing by VR1. So I would write minus VR1. And then over R2, I go minus VR2. And I'm back where I started, so that equals 0.
So when you did it in your head, you treated this sort of bottom area here almost like the ground. And some way people like to think about it is saying that the change in the battery Vn must equal the height change of the other 2, kind of when you're doing this height change analogy. Okay, I like to do it a third way, which is seems a little non-intuitive to beginners, but it allows you to not get confused when you're dealing with very large circuits with loops everywhere. And so what I'm going to do is going to seem a little hokey, but it always works. So start somewhere, it doesn't matter where, but I'm going to start the same place you did, right, at the negative terminal of the battery, and pick a direction you always go in for that whole circuit, and this is important. So I'm always going to go clockwise, which is, of course, the same thing we did a moment ago. But and then what I'm going to do is, as I hit every component, I'm going to look and pick the sign that I see first without thinking, really. So here I get up to the Vn and I see minus, so I'm going to write minus Vn. And I see the resistor, well, I see plus as I'm going, right, I'm coming around and I'm going clockwise, I see a plus, so plus VR1, and then I keep going around the loop, another plus, plus VR2, and that equals 0.
So that's very good. It looks like all three of these methods brought us the same answer.
Yeah, exactly. I mean, this is all the same thing. We just wanted to show them several ways of doing it. I'm a big fan of this one, even though it seems weird to beginners. And in many high school and physics classes, you learn it this way because it's a bit intuitive, right? That you went up by this much and then back down by so much. But anyway, this is our first equation. This is KVL.